All right, guys, so let's take a look at a code-based approach to the problem. So the way that I formally talked about tackling this was by dividing the problem into two portions, solving for the equalities first and then the inequalities. So let's take a look at solving for the equalities first. So kind of like most other problems, I'm going to set my variables like meets satisfiability set to true, the size of the English language being 26 characters, the globally unique ID being based on the size of the English language. Actually, we can set that value to a 0 and this will still work. Flag value and a couple of other extraneous values that turns out they are not actually needed here. All right, so let's go through the first portion, which is to loop through the equations with the equality and construct an adjacency list. So in this example, right, I'm going to create an edge list, so I'm going to instantiate a dictionary. And for every equation in the equations, I will extract the source, the destination, and the symbol. And now, luckily, for the symbol, it turns out even though the equality and the inequality are two characters, we only need the first character because an inequality begins with the exclamation mark, but the equality begins with an equal sign. We ask, okay, if the symbol is an equal sign, if the source and the destination are not in our adjacency list, we instantiate a key entry to an empty set, and then because this is a bidirectional graph, for a given source, we add the destination as a child member of the adjacency list, the children, and we add the source as a child to the adjacency list set for the destination. Note that this is only for the equations that are equalities, not inequalities. So for example, if I'm given equalities like A equal to B, A equal to C, A equal to D, and B equal to C, our adjacency list will resemble the following: A, B, C, D, B, C, D, B, A, C, C, A, B, and D, which goes to only A. All right, so that's the first portion. The second portion is to set a values in a global hash map. So that's based on the DFS in the adjacency list. So we create an empty dictionary called valmap, and we create a visited set. And we also leverage the use of a globally unique ID that's always incrementing. And the reason why we're going to do this is that for every connected component in our set of equations, so let's come back to slides. For every connected component, like in the figure here, for the first figure, we're going to do a DFS, and we're going to set every node that is reachable from a given node in the connected component to the same value. So we're going to keep track of a visited set, and we'll ask, okay, if node A is not yet visited, we DFS from A to every node reachable from A, and we assign it a unique value that is the same. So we set A to 1, B to 1, C to 1, and E to 1. We do this for all other connected components like CC2 over here, G to H to I, where instead of using 1, we use a 2 because we want to note if the values can be unequal if we had to test inequalities in the future. So we want values within connected components to be the same, but we want them to be distinct across the connected components. So coming back to the code, if it's not visited, we do a standard DFS, and in this case, we're doing a queue-based, we're actually not doing DFS, we're doing a BFS here using a queue with a frontier that we explore and iteratively exhaust in a standard BFS manner. All right, it's actually in the last step that's the meat of the question, which is the handling of the inequalities. So this time we go back through our equations, but we don't go through the equal cases since we already have our data structures set up for that. Just like in the graph, we go through our unequal cases. So we extract the same set, we do the same set of pre-processing steps, But this time when we find that the symbol is unequal, we have to ask ourselves two questions in a minified rules engine. The first being if it's unequal and the source is equal to the destination, such as A not equal to A or B not equal to B. In those cases, we have an immediate failure because a node can never not equal itself. Nodes must always equal themselves. That's an identity property. In the other case, we have to ask ourselves first if both the source and the dest are nodes that are actually encountered, because we could have an inequality where the nodes don't actually exist. Like if I gave the case of A not equal to K, K is not, or A not equal to P, A not equal to Q, Q is not a connected component because we don't have an equation, an equals equations for that, but we need to say that it will hold true that A is not equal to Q because Q doesn't exist in our space here. Q can take on any value. Coming back to that same conditional logic in the rules engine, we asked ourselves, okay, if both the nodes are in this value map, we extract the corresponding value that we assign to them in our connected competence BFS traversal, and we ask if those values are equal. Because if those values are equal, that indicates that we broke inequality. We cannot have we are looping through inequalities, and the only case where an inequality holds false is when both sides of the inequality are the same value. So we can immediately meet satisfiability to false and break out of this loop. Otherwise, we continue processing every other equation in the loop until we check every inequality. At the end, we return a single Boolean meets satisfiability, true if all equations can be solved, and false otherwise. Alright, so now let's talk about the final aspect of this problem, complexity analysis in big O. We have two variables that we want to analyze for big O, time and space. We first set our variable soup. Let E being the number of equations and let V being the number of nodes in the graph, which at max can equal 26, which corresponds to 26 lowercase English letters. The time complexity for this approach overall is O V plus E plus O of E. The reason being that the first loop going over the equalities and the last loop going over the inequalities is O of E time, where E is the number of equations. In the next case, actually, let's kind of let X be the number of edges in the graph. But in the middle, we have one last condition, which is having to check every node in the graph and doing a DFS from that node through every possible edge that node can be connected to. In the middle portion, where we set the unique values across each connected component, we have O V plus X time, where X is the number of edges in the graph. As for the space complexity, we have O V plus X for the adjacency list, which is every node and its children, plus O of V space for the value that we assign to each node. Like if we come back to the diagram here, we can see every node, like A to I, needs to have a unique value, needs to have a value assigned to it. We also only do, since the approach is iterative and does not involve multiple function calls, it's going to be O of one implicit call stack space. Now, of course, you could make this recursive if we came to lines 39 to 51 and we asked to code this using DFS or BFS function signature style calls, which would change the implicit space but does not change the explicit space or the time performance of our. Alright, so that's a wrap from me. I hope that these that my videos, part 1 and part 2, was super useful. I am wishing you guys the best of luck in preparing for upcoming interviews or non-sites and or on-sites, whether it's a main company or other companies out there. All right, take care everyone, and wishing you all a good day.